Hey guys, and so this is a follow-up to my proof on square root of three's irrationality. I was very much proved wrong. So we're gonna follow this up with I hope this is a revised proof. I hope this is actually correct this time. So we're gonna start by erasing a lot of the work I did because it was all wrong. I'm gonna get rid of this. I'm gonna get rid of this. And we're gonna make a couple new assumptions because I was very much wrong and feel kind of dumb about it. So this is still good. Square root of 3 is equal to m over n, where n is not equal to 1 or 0. But now m over n is also a reduced fraction, as essentially a fraction in its simplest terms. I'm going to say reduced. So now we have 3 is equal to m squared on n squared. We just squared both sides. Multiplied by n squared, we got 3n squared equals m squared. Now what we're going to do here is we're going to consider two cases for odd and even n's. So for odd, or let's start with even actually. For even n, well let's think about a couple examples. For instance, if we plug in 2 for n, we get 4 times 3, which is 12, which is good. 12 is an even number. So for even n, we can, generally speaking, n squared, if n is even, will result in another even. We're just multiplying two evens by itself. So if we had, like, for instance, 2 squared, we're just adding 2 plus 2. And generally, when you add multiple even numbers, if we want to go into group theory, the set of all even real numbers is, I believe, closed under addition, meaning an even number plus an even number. So it's going to get you another even number. We know that repeated addition is multiplication. Repeated multiplication is exponentiation. So we can say that for even n, 3n squared is even. Now for odd n, let's think about that. Let me write that. So now for odd n, let's consider our first odd number, 3. 3 squared is 9 times 3 is 27. So let me finish the sentence actually. For odd n, 3n squared appears to be odd. And if we think about that, also under the lens of group theory, are the odd numbers closed under addition? The group of, or the set of all real odd numbers. Let's think about that. 3 plus 5 do not be odd. So it's not closed under addition. But 3 times 3 is 9, 5 times 5 is 27, 7 times 7 is 49. These numbers are, in fact, odd, so we're going to say 3n squared is odd. So now we're going to put this back into our fraction, just 3n squared over n squared. So we're going to have 3n squared over n squared. And now, if we consider just evens, we know that n squared, as I said earlier, is even. 3n squared is also even, so we get even over even, which is reducible, meaning that m over n is not reduced. So we have a contradiction, meaning that, at least for even n's, it appears there's a contradiction. So that's the first half of our proof. Let me finish the sentence. Reducible. So there's a contradiction there. And of course, now while it's not necessarily true that odd over odd is reducible, for instance, if we had like 5 over 3 or 7 over 3, that's not necessarily reducible. But what we have here, because there's both an n squared in the numerator and the denominator, is that we have, this is even n. Now we're going to have 3n squared over n squared. This is going to be odd. So this is odd ends. Odd ends, we have 3 times an odd number. And, well, an odd number is square, but it's odd. The point is the number comes out to be odd, which of course is reducible because these numbers are the same. We have n squared in both numerator and denominator, so squaring it, squaring the same number is, going to get you the same number. So multiplying that by 3, if we do an example out, we have, for instance, we plug in 5, we got 75 over 25, which is very much reducible. So this is also reducible, meaning that our original assumption that the square root of 3 can be expressed as a fraction m over n, which is already reduced, is wrong. So we have a contradiction there. So there's a contradiction, and I believe that that covers both cases. I hope it does. I'm not entirely sure. But it seems like we have a contradiction here, and so our proof is maybe now complete. I don't know. I could still be wrong. If I'm still wrong, feel free to tell me, but I believe this is a better proof than my original one. So yeah, thank you for watching.